All right, let's continue where we left off. So last time we were talking about metric spaces. And we saw that they're basically just sets with a distance function, and the distance function, well, the function, in order to be a distance function or a metric, is required to satisfy certain properties. Okay. And we looked at some examples. We saw that Rn is a metric space with this so-called standard metric. Um, and whenever you have a metric space, any subset of that is also a metric space. That's the metric is just given by the metric of the bigger metric space. So sometimes that's called the induced metric. Right? Okay, now this time I want to talk about open sets, open and closed sets. And this is very important because open and closed sets are sort of the building blocks of analysis. So open and closed sets. Okay, definition. So let's say E is a metric space. And let's say that P naught is an element of E, and R is a real number, a positive real number. Okay. Then the open ball in E of center P naught and radius R is, well, it's written like this. P0, and this is defined to be all elements P and E such that the distance between P naught and P is less than R. Okay, and the closed ball again in E, right, of center P naught and radius R is, I don't have a notation for this, but it's all elements P and E such that the distance between P0 and P is less than or equal to R. So the only difference between an open ball and a closed ball is this, the inequality. Right here it's strictly less than R, and here it could be equal to R. So in particular, the open ball of radius R centered at P naught is contained in the closed ball. Right? The closed ball just consists of the open ball together with elements whose distance from P naught is equal to R. Right, let's look at an example. Well, in R2, the open and closed balls just look like, so here's P0, and let's say that you have some radius R. Right? Then you're just looking at points whose distance from P0 is less than R. So this would be, so all the points here, right, all these points inside here, this is the open ball centered at P0 of radius R. Now if you had a different point, like P1, say, different radius r prime, okay, what would be the closed ball? Well, it would be all elements whose distance from P1 is less than or equal to r. So this time, we sort of include the boundary, right? So it's all the points here together with the points on this boundary. So this is the open ball, and this is open, this is closed. Now let's say that we took a subset of R2. So let's say that we took the metric space E, which is all elements x and y in R2 such that x is positive and y is positive. Okay, so we're looking at the first quadrant, right? So E is the first quadrant. Now what would be a closed ball? Let's say that you are here. So let's say this is P naught. And you want this to be your R. Well, if we were looking at the metric space R2, then the closed ball centered at P naught of radius R would be this entire circle. However, right, if you look at the definition of a closed ball, it's all elements in E in the metric space such that the distance is less than or equal to R. So if E is this, right, if E is only in this first quadrant, then you're looking at all the points in the first quadrant whose distance from P naught is less than or equal to R. So that would be this. All the points here, including this part of the boundary, but since the x and y axes are not part of E, they are not part of the closed ball of radius P naught of radius R centered at P naught. So that's what a closed ball looks like. Here now, of course, if you had a closed ball like here with a smaller radius, then that would be fine. Then it would just be this. So in general, if S is a subset of E, so let's say E is a metric space and S is a subset with the induced metric, then a ball of radius P naught, not radius P naught, centered at P naught of radius R, right, in S, so this is the open ball in S, it's just the open ball of radius P naught in E intersected with S. Right, so in this example, okay, this picture is not scale. Yeah, it's okay. Well, this picture in this example here, right, this closed ball is just the intersection of the closed ball in R2 with E. Okay. By the way, why is this fact true? This is just from the definition, so it's something to kind of think about. All right, now let's look at an example in R1. In R, okay, so let's say that you have an open interval AB. Now I claim that this is an open ball. Okay, why is this an open ball? Because, well, to show this, we need to show that there exists a P naught and a radius such that this interval an open ball? Okay, well, it's an open ball because A and B is equal to the ball of what radius? Well, if you take the midpoint here, right, this is going to be A plus B over 2, and then you just have R is equal to this distance, right, R. So this is the ball of radius R centered at P naught, where P naught is A plus B over 2, and R is A plus B over 2 minus A, which is B minus A over 2. Right, okay. And similarly, if you take a closed interval, then that is a closed ball with the same center and radius. So the notion of an open ball generalizes the notion of an open interval. Okay, that's an open ball. That's open ball and a closed ball. Now let's talk about open sets. So this leads to the next definition. A subset S of a metric space E is called open if for every element P and S contains some open ball of center P. Okay, fine. And we'll see that every open ball is an open set. And once you have an open ball as an open set, we can actually come up with more open sets by using the following proposition. So this proposition says, for any metric space E, first of all, the empty set is open. Okay, the subset E is open. The union of any collection of open subsets of E is open. And lastly, the intersection of a finite number of open subsets is open. Okay, let's prove this. So why is the empty set open? And by the way, when we say open here, when we say for any metric space E, blah 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 is open, what we really mean is that this is open in E, right? So if you look at this definition, okay, maybe we should just be more precise here. A subset S of a metric space E, so you have some metric space E and some subset S. It's open if for every P in S contains some open ball of center P. Now when we're talking about some open ball, we're talking about open in E, an open ball in E of center P. Okay. open ball in E of center P. Okay, so let's go back to the proof of this proposition. So why is the empty set open? Well, okay, what will we have to prove? So we'd have to prove that for every element of the empty set, there is an open ball centered at that point that is contained in the empty set. However, this is trivially true because the empty set has no elements. So it's true that for every element, blah 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 happens. So this is just trivially true. The second one is that E is open. Okay, why is this true? So again, we need to start off with an arbitrary element and show that it contains an open ball. We'll just take any r greater than 0, then the ball centered at P of radius r is contained in E by definition, right? I mean, the open ball by definition has to be contained in E, so it's an E. So therefore E is open. Okay, number 3, the union of any collection of open sets of E is open. Alright, so to do this, we could say, so suppose that you have a family of open sets. This be a collection of open subsets of E. Now you want to show this is open, so we need to show that your union contains an open ball. Well, just okay. So let P be in the union of the U alpha. By the way, in case you're wondering what the A is, right? So if we have a collection of open sets, we just let A be any indexing set. So this is how we describe a collection of open subsets, which might not be countable, right? It's just we use an indexing set. So let P be an element of this union. So we want to show that it contains, that there's some open ball centered at P that's contained in the union. Well, since P is in the union, then then there exists alpha in A such that P is contained in U alpha, right? Now U alpha is open, so since U alpha is open, there exists some r greater than 0 such that the ball centered at P of radius r is contained in U alpha. Right, and now why are we done? Well, because the union of the U alphas contains U alpha. This is a subset of the union of the U alphas. And that proves number 3. Okay, number 4 has the property of illustrating a nice technique. So we want to show that the intersection of a finite number of open subsets of E is open. Okay, so we need a finite number of open subsets, so let S1 through Sn be open subsets of E, and let P be in the intersection so we want to show that there is, let me draw a picture just to illustrate what's going on. So you have, like, let's say that n is 2, and let's say that this is your S1, and this is your S2, right? And you take a point P in the intersection, so that's P. And you want to show that there's some epsilon that's, or some R such that the ball of radius R centered at P is contained in the intersection. Well, the idea is that you know that that since P is in S1, there's going to be some ball centered at P that's contained in S1. And you also know that there's going to be some ball centered at P of some radius that's completely contained in S2. And then the idea is to take a small ball that's contained in the intersection, right? And then it'll be in both S1 and S2. That's the idea. So going back to the proof, okay, let P be in S1 through Sn. So for I from 1 to n, each Si is open, so there exists some real number Ri greater than 0 such that the open ball of radius Ri centered at P is completely contained in Si. Right? Then let R be the minimum of R1 through Rn. Well, then the ball centered at P naught of radius R, P of radius R, is completely contained in the ball of radius Ri centered at P for all I from 1 to n. That's because, okay, why is this true? So that's because if you have an element P and then you take a radius R, say R1, and then you take a radius R that's less than R1, right? This thing is contained in that because if I have an element whose distance from P is less than R, in particular its distance is less than Ri. Okay? So this open ball of radius R is contained in the ball of radius Ri for all I, and so therefore it's contained in S1 through Sn. So S1 intersect to Sn, which completes the proof. Okay. So more on open sets and closed sets later.